So I thought, in a Lego game-like fashion, if we make them and then mix them, we should be able to form this one. I went into the library and checked the literature. Crazy. I had a mission, so I was very carefully searching literature. And then I summarized the state of the art back then. So when we use these kinds of unsaturated group containing electrophiles, they virtually never work. Of course, without any catalyst, okay? That was before catalyzed cross-coupling. And these would work, but they are sp3 carbon-containing or acyl one. But they sometimes work, but all kinds of side reaction, elimination, beta elimination, so on and so forth. So this is a picture back then. And then I decided to, so now, with the introduction, today I don't talk about this, spend any amount of my time, only briefly. Eventually we found this palladium catalyzed cross-coupling. And now all red part is all green except this one, which is still, so I paint this yellow. And most of the other areas are mostly green because thanks to younger people, Buckford and anyway, my friend, Chinese friend. So thanks to their activities, this thing is becoming greener and greener, but not as green as the. There is one no area back in the middle, 3x3 matrix. This is where aryl and aryl electrophiles and aryl metals are to be mixed. But luckily, the kinds of products that you obtain by this process, you can also obtain them this way, just by shifting the point of CC bond formation. So they work so well, so normally I advise against these, but some of these have become available in a satisfactory way with time. But the question is, why metal? I should be careful not to spend so much time. Well, so here is a 8 electron 2468, 8 electron, so-called coordinatively saturated organic compound, and unsaturated double bond. Then if you try to mix them and then try to achieve some addition between the two, no facile reaction as you know, but once you switch this 8 electron alkane and convert them, or use 6 electron, 246, with one empty orbital, with a plus charge, of course you have to adjust this. And then this reaction goes wild, carbocation. So you see the power of this empty orbital. I might say low-lying, readily available empty orbital. No wonder my Professor Brown, hydroboration goes so rapidly. It goes well at 0 degrees, which we usually use. Minus 25, it still goes fast. Minus 50, minus 78, still goes. Tremendous difference between this and this. And that can be attributed to the ready availability of this empty orbital. You know, everything is rational in science. I think in chemistry, everything is 100% rational if we become equally rational. Anyway, so you can explain that. And no wonder you replace boron with D-block transition metal element like zirconium. So here, of course, because you use D-block transition levels. You have to count up to 18 for full coordinative saturation. And then 16 electron, this zirconocene hydride undergoes hydrozirconation almost as readily as hydroboration. And the critical part, if you just look at the critical part, they are very much alike. Okay, so now we understand, of course, you learn all these things. But here's something that you should have learned, and if you haven't, then I want you to learn this. In Xiamen, China, a group of theoreticians, they published in a reasonably well-recognized journal not so long ago, about 10, 12 years ago, this paper. Then they analyzed the reaction of acid and the base in general. We learn in class, if you mix acid and base, bingo, you observe neutralization, you get a salt. But they said, this might be true in a thermodynamic sense, but the simple acid and base reactions struggle in kinetic sense. This is something that we should know. You know, if you mix HCl and NaOH, of course, that's a very, very favorable case. But in general, we should know that simple acid-base reaction has a surprising hindrance. Have you ever thought about that? This is very, very important in organic synthesis. It goes like this. Now A acid and the B base, they approach, and the base begins to transfer electron. As it does so, then A will acquire the electron, negatively charged electron, so it will be negatively polarized. B, by sending an electron, it will become less and less basic, so it will be positively polarized. What are this effect of polarization? Of course, negative charge will start repelling electrons, and the positive charge will start attracting electrons. What is the overall effect? First, B says, go to A to form a bond. Now, don't go, come back. You can really see the kinetic barrier rising. So this is a very, very general kind of situation. HCl and NaOH, no problem. They overcome this barrier and then go to the better destination. But in many cases, we may encounter this, and we should be prepared for dealing with this. So this is in their theoretical. And I was thinking along this line for maybe 10 or 20 years before I finally found this paper. And I learned reality shown here. So how would you overcome this? Any student having a ready-made answer? If you're right, I will have a Purdue t-shirt for you. Anyone? Anyone dare say dare try this? You touch your head. Okay. In view of time, I'll go. Go ahead. One way to electron transfer between acid and base. There's an intrinsically high kinetic barrier. This is one thing that we should learn from the Xiamen professor. And I was sensing for about 2 decades before finally I read it. And I was only sensing, but I didn't have a good answer. So what is the solution? Make it 2 ways. make it two ways, not in the same direction, but in countering direction. Two electrons go from left to right, another set of two electrons going in the opposite direction. Then the ill effect that we just discussed, all but cancel. And overall, they will lower the kinetic value. You know, these simple things are so important in trying to discover new reactions with your own. So here it is. Actually, the answer was already there, which I just didn't know. Most people don't interpret it in the correct way. So here's what we call a Duer-Chott-Duncanson model. Duer-Chott-Duncanson model. And MJS duo. But he got the cue, he got the idea from Fukui. So Fukui, during the World War II, I understand he was doing this kind of thing with, hand cranking calculator. And he published in 1951. In 1952, year later, his so-called homo-lumo theory. That was embraced by Duer, and Duer proposed this so famous Duer-Chott-Duncanson model. So in this model, there's an olefin here. Okay, CC sigma bond. CC pi bond is shown here. That's usually what we learn, but Fukui said that's not enough. That's not enough for understanding the chemistry. So in addition to this pi bond, you have to think of yet another orbital right above this pi orbital. He named this one LUMO. That's his invention, his discovery. Lowest unoccupied empty orbital. It's butterfly shaped like this, as we know. Now, with this pair of these two, you can readily understand two electrons can interact with a Lewis acidic metal, and when they are strong acid and bases, then they may form a salt. But that process can be greatly facilitated if the metal itself has a LUMO, not a LUMO, but a low-lying orbital, like this. Well, I just use the transition metal ones. Go ahead and use this. Then as two go up and two go down. So that is Fukui's, based on the Fukui's homo-LUMO interaction theoretical chemistry, which was embraced by Duer next year, 52. He published this Duer-Chott-Duncanson model. Why is this so great? Well, by now, of course, people in this room will know that ill effect, maybe I should go back again. Ill effect, I just explained here, don't go because of this polarization, don't come because of this negative charge development, electrons are negative. So these are compensated by devising two level. So two electrons go up, and if you consider a LUMO, and then D block transition metals can have many of these kinds of orbitals containing electrons. They can back donate electrons. So that ill effect can be all but cancelled. This is the essence of, at least one of the very, very important essence of D block transition metal catalyst. Now I can stop my talk here. But let me just go on. Now let's look at the hydroboration, or any kind of hydrometallation that can be represented by this scheme. Now here, 2 electrons go up, just like this one. But then metal hydride containing 2 electrons can be back-donated. So this back-donating hydrometallation. No wonder they are so fast and so stereo-selective. Well, everything goes within a molecule, in a organized way. Hydroboration, 100% cis addition. Many other hydrometallation reactions are essentially 100% syn addition. We understand this. Okay, then I thought, if this mechanism is so important and so correct, we should be able to replace this hydrogen with what? With any element. That was my young guy's reckless idea. We should be able to replace this one because the main action is here. So just retain this one. Yeah. What else you have in the periodic table? Of course, we are most interested in carbon. So put the carbon here, and then I say, what's wrong? Then this should be a general scheme for all kinds of carbometallation. So I named this one carbometallation. You consider this to be a reasonable naming? If you come up with something before someone else, actually it's very difficult. This reaction was known already in a Ziegler-Natta polymerization. I was a polymer major, so I knew that. But anyway, so I started calling this a carbometallation. Nobody is against me right now, but I was attacked by American, Japanese chemistry authorities, the senior people. What is carbometallation? You shouldn't introduce a new chemical terms cheaply. So you should call this just addition reaction or something like that. So I said, well, I believe that this is a very fundamentally important process in chemistry. And if addition of metal, hydrogen and metal is called a hydrometallation, addition of carbon and metal in a similar way may be called the carbometallation. So I defended my choice of this word. If you start, more or less start working in unknown or new area, you get to name. That's an interesting fringe benefit or bonus. Then I didn't stop here. There are all kinds of elements in the periodic table. So we can put metal here. And I call this metallometallation. Even this reasonably sounding name. But now many people accept this metallometallation. Then what else do we have in the periodic table? I think we get to use about 70 or so, I told you. Halometallation, with a halogen. Okay. There is fundamental difficulty in this reaction. Can anyone, any young mind, tell me what might be of these things uniquely disadvantageous to have a halogen or highly electronegative element? Can anyone tell me? Someone's hand was raised up to here, but not. No, please. Well, of course, there is a kinetic issue in chemistry, and we were sort of dealing with a kinetic issue. But of course, more basic is a thermodynamic issue. Thermodynamic issue. And as metal is bonded to hydrogen, okay, carbon, okay, but halogen, or X meant to be electronegative, more electronegative, then this bond is thermodynamically much stronger. And this reaction may become contra-thermodynamic. That's a big no. That's a big no. So all these are thermodynamically downhill, but this one can become thermodynamically uphill. Then we don't observe. But you can never say never. Already shortly after Brown's hydroboration discovery, in UK, I'm forgetting these names. UK, I think Welsh professor reported bromoboration reaction. He was right. Bromoboration reaction. So you should never say never. So apparently bromine and boron are somewhat weaker bonds. So bromoboration must be thermodynamically downhill. It's got to be, of course. And then, more importantly, as you would have by now acquired this predictive power from my teaching at the graduate level. So in trying to teach at the graduate level in the most serious way, I needed to learn myself. So those days I learned a lot, and then out came lots of ideas. Okay, then I tentatively summarize. There are 4 basic processes using D-block transition metal, or probably with or without, but let's say with just